Hello, I'm H.Ishibashi from Kyushu Institute of Technology. I'd like to talk about a stopping criterion for Bayesian optimization by the gap of expected minimum simple regrets. Bayesian optimization is a framework for efficiently optimizing a costly to evaluate black box function, and it has been applied to various optimization problems. The algorithm of BO consists of 3 steps. In the first step, BO estimates the posterior of the surrogate function from dataset. In the second step, BO selects the next point that minimizes the acquisition function. In the last step, BO calculates the value of the objective function and updates the dataset. By repeating these 3 steps, BO efficiently finds the optimal points. Our interest is when is the best timing to stop BO. If BO is stopped too late, the efficient search becomes meaningless. On the other hand, if BO is stopped too early, we cannot find the optimal point. So stopping time of BO affects an efficiency of BO significantly. If we know the minimum value of the objective function and desired threshold, we can stop BO by using the simple regret. But the criterion is not realistic because this is not known in general. In this work, we propose a stopping criterion for BO based on the gap between the expected minimum simple regrets. The proposed criterion stops BO when the upper bound of the gap is below the threshold. In our approach, we can prove that the upper bound converges to 0 and propose the adaptive threshold and heuristic threshold. Our approach considers the expectation of the minimum value of the function sampled from a posterior distribution of surrogate function, which is referred as the EMSR. The behavior of the EMSR is similar to that of simple regret. So, this study determines the convergence of BO by evaluating the gap between EMSRs. But EMSR requires the global minimum of the objective function and expectation of global minima with respect to sampled function. To avoid the difficulties, we evaluate that the upper bound of the gap between EMSRs converges to 0. The derived upper bound is like this. In the upper bound, the third term is dominant. So, roughly speaking, the upper bound becomes a product of the upper bound of the simple regret and the Kerr divergence between posterior distributions. The proposed stopping criterion stops BO when delta R tilde T less than threshold ST. Then we can prove the upper bound converges to 0 with a high probability. So we guarantee that the proposed criterion converges to the stopping criterion based on the gap between the EMSR for any choices of threshold values with a high probability. The remaining issue is how to set the threshold. We propose 2 threshold determinations. One is the adaptive threshold. The threshold is derived by evaluating the bottleneck of the convergence of the proposed upper bound, and the threshold can be interpreted as stopping BO when the upper bound of noise effect exceeds delta R tilde T. The adaptive threshold provides a practical benefit, but we may want to stop early or we may want to find optimal points more rigorously, depending on the cost of the objective function and other factors. The heuristic threshold is used when a user wants to control the stopping timing with some domain knowledge. In experiments, we applied the proposed criterion to test function optimizations. then the proposed criterion tends to stop BO after discovering the optimal points for most test functions. Next, we apply the proposed stopping criterion to hyperparameter optimization of machine learning models. Then the proposed stopping criterion tends to stop BO when BO finds the semi-optimal parameters, unlike the conventional methods. For more detailed experiments, please read our paper. Thank you for listening.